Hi everyone, my name is Neha, and in this lecture we are going to learn about encoding, decoding and 7-segment displays. So let's get started. So these are the topics which we will be covering in the lecture. We'll be covering BCD code, the access3 code, gray code, application of gray code as a shaft encoder, ASCII code, encoders, 7-segment displays, 7-segment LED, decoders, BCD to 7-segment decoder, LCD vacuum fluorescent displays. So let's first start with BCD. So BCD stands for binary coded decimals. We have seen binary coded decimals in the initial lectures. So a BCD number is a 4-bit binary group that represents one of the 10 decimal between 0 through 9. So I hope you remember that how to convert a number from decimal to binary. So one example is given here. We have a decimal number 4926. So if we are asked to convert it into BCD, then the output will be this. So as you can see that this is going to be the BCD code for this decimal number. And if you follow 8421 BCD method, you can easily calculate the binary number for these particular decimals. So for example 6. So this is 1, 2, 4, 8 place values. So 4 plus 2 makes up your 6. So that's why you have 1 1 here and rest of them are 0. And then 2 is here. So that's why you have 2 here and rest of them are 0. And then you have 9. So 8 plus 1 makes up 9. So that's why you have 1 1 here and rest of them are 0. And then 4 will be 1 and rest of them will be 0. And this makes your decimal 4. So this method is super easy. If you're dealing with like a small numbers, you can easily calculate into a binary number. Now let's see next. So we have a quiz question here. It says convert the BCD coded number into a decimal. So our binary number is given. We have to convert into decimal. So here also you can use the place value method. You know that this is going to be 1, this is 2 and 4 and 8. So based on that you can calculate which number is which. So for this case you can see that 1 is there only at a 1's place and rest of them are 0. So this is going to be 1. And then you have 1's on 1's place and 2's place and the 4th place when it is 4 here. And then here it is 0 at the 8th place. So if you add them up, this will come out to be 7. And here you see all these 3 are 0 and this is 1. So at the 8th place value, so this is going to be 8. 871 will be your answer for this particular BCD code number. Next, we have 350, which is a decimal, and the answer is already displayed here. 0 is very simple. It's going to be this. For 5 is 0101. You can calculate also. So at this place value is 4. This is 1. So 4 plus 1 makes up 5. And then you have 0011. So this place value is 1. This place value is 2. 2 plus 1 makes up 3. So this is the binary equivalent of this decimal number. Now we are going to see access3 code. So this is one type of another type of code which is used in digital electronics, and to convert a decimal number to the access3 form, what we do, we add 3 to each digit of the decimal number and convert to the binary form. So you understand, like you have a decimal number. So let's see this table, and by that we will have a good idea. So we see that we have the decimal here. All the decimals from 0 to 9 is mentioned here. And this is the binary conversion of each decimal number. And to find the access3 code, what we have to do, we have to add 3 to each digit of the decimal number. So if you add plus 3 to 0, that will make up your 3. and if you convert that 3 into binary, that will be your access code. So this 0011 basically represents your 1 in access code. Okay, and let's see one more. So you have like 1 here, so 1 plus 3 is 4, and 4 in binary is 0100. Okay, so this is your 1 in access code. If you have like a decimal 1, then the access code number will be this for that particular decimal. So let's move on to 4. So 4 plus 3. So here you see is the binary of binary conversion of 4, which is 0100, and if you add plus 3, so 0011 is 3. So this plus 3 in a binary is given all here, and if you add this to this, then you will have 0111. And in decimal, you know that 4 plus 3 is 7. So here it is 7. And then this is actually not 7. In binary it is 7, but in access code, this binary number, binary number basically represents your 4. So let's see one more example. For 9, if you plus 3 to the 9, so 9 plus 3 will make your 12. And so 12, so this is your 9 and this is your plus 3. If you add this 3 binary number of 3 with this one, you will get 12. So this represents your 12. Now let's see some sample problem. So we have to convert decimal 359 into access 3 code. So at 9 you will have 1100. So that's what you have for access code. At 9th position, the decimal 9, you have access code 1100. That's what you see here. And at 5, let's see what we have. At 5 it is 1000. So that's what you have here. And at 3, so at 3 we have 0110. So this has been put here. So this total is basically represents the access 3 code for this decimal value 359. Now let's do a quiz. To form an access 3 coded number, decimal 3 is added to the decimal number and this is converted to its 4-bit binary code. Is it true or false? It is true, because decimal 3 is added to the decimal number, and that's how we convert it into a access 3 code. Now next is the access 3 BCD number 10100100 equals to what in decimal. So if you look back into the access 3 code table, then you will realize that this 0100 represents your 1 and 1010 represents your 7. So answer is 71. The decimal number 428 equals what access 3 number? So at this point I would ask you to pause the video and look back to the access 3 table and see if your answer matches with mine. So I hope you have matched your answers by now. So the answer is this. So 8 will be equals to 1011 and 2 is 0101 and 4 is 0111 in access 3 code. So this was the access 3 BCD which you have seen. Now next is the gray code. So let's see what it says here. The gray code's most important characteristic is that only one digit changes as you increment or decrement the count. So let's see. So on the right you see we have a gray code here, and it is converted from a decimal. So this is a decimal from 0 to 16, and for each decimal the gray code is given, and as you keep checking the gray code, then you will realize that in each increment or decrement, like as you go, you will see that only one digit is changing. So for example, from 0 to 1, this 1 is changed, and that made your this decimal as 1. And then from this binary number to this binary number, you see that only here 0 has been converted into 1. So, and this 1 and 1 it has remained the same. And so and then further we have 3, and in 3 also, so this 1 is same, and then this 1 has been converted into 0, and then further 1 and 0 has remained the same, and then this 0 has been converted into 1, and then so on. If you just keep looking, then you will realize that every time, like every count, your only one digit is changing. So these gray code, they cannot be used in arithmetic circuits. The gray code is used for input-output devices in digital systems, and gray code is not classed as one of the many binary coded decimals. And if you notice that it is quite difficult to translate from decimal to the gray code. If I ask you to convert it from a decimal, then it would be really difficult, whereas with the BCD it was quite simple. And then back again from the gray code to the BCD is also complicated, and so there is a method for making this conversion, but we usually use electronic decoders to do this type of job. So that's the better solution. And now let's read these 2 points. It says the gray code is commonly associated with input-output devices such as an optical encoder. So so the application of gray code is in the shaft encoder. There it can be used. So each position, angular position, can be defined by these binary code, these gray codes, and that we are going to see in the next coming slides. And then third point says the gray code is not a BCD code. So we already learned that gray code representation has its own uniqueness, and it is not as same as a BCD. Now, quick quiz. The gray code is not a type of BCD code. Is it a true and false? So we just saw that it is a true statement. So the answer is true. The most important characteristics of the BCD gray code is that only one digit changes state as you increment or decrement the count. So that happens only in gray code, and that's what makes it unique. And then third is the gray code is commonly associated with input-output devices such as an optical encoder of a shaft's angular position. So is it true and false? It is true that in shaft encoder we use the gray code in order to determine the angular position. So this is true. So there's one thing I would like to go back and tell you that so you saw already that in this gray code, as we were counting and going down or going up, you saw there is only one digit is changing. So now we are going to observe the same change in the BCD. So you should have you can pause the video and put up a BCD list and compare the different how it is changing as you go up or down or like increment to the next decimal value, then how it is changing. So for that I'll take an example. I'll take an example of 5. So 5 in BCD is your 0, 1, 0, 1. So this is your in BCD. And if you see 6 in BCD, it is your 0, 1, 1, 0, 0, 1, 1, 0. Please excuse me my my handwriting. So If you notice here, as we are incrementing from 5 to 6, you can see uh, you can compare. So this was 1 has changed to 0, 0 has changed to 1, 1 is still same, 0 is still same. So as you're going from 5 to 6, you saw that two numbers, they have to change in order to get into, like, in order to create a new number or get into the getting into the next decimal number, right? So you see there are two numbers change, whereas with gray code it's so easy that you just have to change one number. So this is the advantage of the gray code also. Whereas in BCD, there might be some cases where when you have to change more than two or more than one digits. Now let's move on to the next. Next we have application of gray code in shaft encoder. So this is a shaft encoder you see here, and then you see these are the stationary lights, and each of these which you see, they are numbered 11, 12, 13, 14, 15 and so on, starting from 0 to 15. These are all segments, and then at some places you see that it is dark. For example, here it is dark, here it is dark, and this is light. So which means wherever it is dark, then the light will not pass through, and wherever it is light shade, then the light may pass through this stationary detectors. So these are basically your sensors which are connected, and the light is and they are connected at the bottom of this shaft encoder plate, and a light is thrown from the top, and then if the light passes through the this light shade, or you can say these are the empty places from where the light can pass through, and wherever is dark, then the light cannot be passed through. Okay, so let's see for this particular segment. This is the second segment 2, which says 0011. So you can see that these are the two lightly shaded areas, and these are the two dark ones. So in these dark ones, the light cannot pass, as it will move, and as it will pass through this detectors. Then these two will be 0, because the light is not passed to the sensor, whereas in these two locations the light has been passed, and that's why for those cases it has been put here as 1. So that's why you have 0011, and this is for the second segment gray code. Now let's see, for this particular case, at segment 10, you have like 111. So all the four subsegments in this 10 segment, they all are 1, which means these all are light and open, you could say, and light can pass through from them to the detector. And then you go on, as you go on, you see that 11 segment, 12, 13, 14, 15, and then 0 to 9, all these are the segments, and each has its own gray code. So 4-bit gray code you see is this on the left hand side, which represented here, and this gray code represent each of the segment. Okay, so you see that, like, at wherever position your shaft encoder rotates, that rotation can be recorded, and it can show that at which position your shaft encoder is at. So rotary encoder rotates with shaft, showing angle of rotation represented by one of 16 gray codes. So angle of rotation is represented by one of the segment from 0 to 16 gray codes, and the light beams shine through clear sections, causing an excuse me, causing a high output. A low output is generated when light is blocked from reaching the light detectors. The detectors output the 4-bit gray code. So this we have already seen. So wherever the light pass through, at that instance, you will take it as high, which means 1, and wherever it cannot pass through, that will be considered as your low or 0. The example is shown for segment 10. The light strikes all 4 detectors, so that's why you have like 1 1 1 1. Now let's see. So this is the question. If light passes through a transparent area of the shaft encoder disk to strike a light detector, a high or low logic is generated. So in that case, we already know that if the light passes to the detector through this shaft encoder, then that will be considered as high, which means 1. So this is your answer. Second is, with segment 9 aligned over the light detectors, the encoder will output the 4-bit gray code of. So at segment 9, so we have to look here. So you see at 9 we have 1101. So 1101 is going to be our output. So our answer is going to be 1101. And then we have with segment 2 aligned over the light detectors, the encoder will output the 4-bit gray code of. So at 2 you will check it out. So you have 0011 here. So you have 0011. And then this rotary encoder can detect the change of angular position of the shaft every 1/16 rotation or each 22.5 degrees. So if you do the math, you will get 22.5 degrees. So this is true because we saw that it is 1/16. So it starts from 0 to 15. That will makes up your 16. So this statement is also true. And you can also calculate the degree by dividing the 360 degree. So you see this is a 360 degree, and then each segment we have, and if you count, you have 16 segments. So if you divide 360 degree divided by 16 rotations, so you will get 22.5 degrees. So each rotation is of that much, 22.5 degrees. So now let's see next. Next question is, the purpose of the rotary encoder is to locate the angular position of a shaft or wheel that might be required by a robot or machine tool. Is it true or false? It's going to be true because you can see how precisely each segment has been placed, which means like if we have a robot, then we can easily detect its motion, like any position where it could be, because each segment has its own code. So with the help of this method, we can easily detect that. So in robots, you might find the shaft encoder to have the precise to find out the precise position. And now next, so this was true. Now next is ASCII code. So ASCII code stands for American Standard Code for Information Interchange. They represent numbers, letters, punctuation marks, control characters. ASCII standard, it is a 7-bit code, 127 characters, and they can be extended to an 8-bit code, which is very popular. And extended ASCII adds graphics and math symbols to code, so that makes up total of 256 symbols. So these ASCII codes, they are widely popular, and they are used to send information to and from microcomputers. The standard ASCII code, you already saw that it is of a 7-bit code, which is used in transferring coded information from keyboards and to computer displays and printers. So for example, the ASCII code for uppercase M is 77. So most computers, they use ASCII codes to represent the text, which makes it possible to transfer the data from one computer to another. So that's the advantage of using the ASCII code, and that's how it has been used. Now let's go to the next slide. So there are a couple of questions here. A common 7-bit code used to represent numbers, letters, punctuation marks, and control characters is known by the acronym which is ASCII code. So the answer is ASCII. Second is the acronym ASCII stands for American Standard Code for Information Interchange. Third, extended ASCII code is an 8-bit or 10-bit code which adds graphic and math symbols to ASCII for a total of 256 symbols. So the answer for this is 8-bit. The standard, we know that it is 7-bit, and the extended one is 8-bit. So that's why we have 8-bit as our answer. So if you want to get in detail about ASCII code, then I would advise you to research a little bit and see like how the codes in ASCII they look like. So this is all about different codes in digital electronics, and we will continue the rest of the topics in the next lecture. So thank you for watching.